Thank you very much for inviting me here, and actually a great pleasure for me to present this work to you. I wish I could be there at ICCV, but I'm in Detroit, as many others. Today, I want to talk about SLAM, of course, but I want to introduce some of our work that we try to integrate the learning with the SLAM. So in the title, I said high-level scene understanding in the non-conventional sensors, and you will see what do I mean by that. So our group, the SLAM, and in doing so, we incorporate many different sensors, LiDAR and camera, but not only that, like for example, the thermal camera or sonar for underwater, radar for a very turbid environment or very foggy and hazardous environment, and even camera. So our group is reaching towards some non-conventional sensors beyond the visible spectrum too. But why we are doing so is to overcome many challenges, not only the visual appearance changes, but also the structural changes too. And today, the three topics that I prepared is about how to overcome those challenges. The first one is I want to introduce how we can use live, little higher level information in the place recognition. More specifically, what we want to talk about is how to handle lines, how can we handle lines better, and how to represent them and match them. And the paper title for this work is "A Line is a Visual Sentence." And the second topic is might be weird to see some manipulation thing in the SLAM workshop, but this is about the pose estimation for a target object. In the manipulation, you need to know the pose of the object to reach out and grasp and do manipulating. And then to do so, we need 6 of pose estimation for the target object. But what we realize is we can change the problem and treat it as an object SLAM, and treating each object as a landmark, and we can solve this one within a SLAM framework. And in doing so, what we try to do is actually we can combine the kinematics with the visual information. So the kinematics can be thought of as odometry, and the visual information making like visual loop closures or in a SLAM. To combine those, what we need is we need covariance or uncertainty associated to each measurement, because the deep learning will give you the predicted mean, but also it'll be nice if it gives you the uncertainty associated with it, so that we can combine that with other factors like, for example, the kinematics or other sensors, right? So that's the second topic that I want to talk about, how to estimate the uncertainty from the deep learning. And the final topic is about the non-conventional sensors that I was mentioning. So our group is heavily investigating using thermal infrared cameras, and we wanted to use the many deep learning for the thermal images for the, like for example, the optical flow estimation or object detection. But the problem that we are encountering is the lack of data. And the question we had is how to secure the enough training data for the thermal infrared images. So the third topic is about how to secure the data set. And also, if it is not sufficient, how can we leverage already existing labels from the RGB image and kind of extracting that from the RGB image by using the image-to-image translation. So those are kind of overview of today's topic, and I want to go one by one. The first topic is about the line as a visual sentence. And I want to make a note that all of the thing that I'm mentioning, we released code and a data set with it. So please visit us, our website, and you can actually see the code and data set. So for this using a line for the visual place recognition, there have been a lot of conventional approach. They try to use a feature point. How do we do that in the computer vision community is considering a word or a feature point extracted from an image as a visual word. And you look at the statistics distribution of the visual word to see if the scene has been seen before. Have I been here before? But what we think is if a point is a word, a line in an image would be a sentence, and the line-to-line matching would be a sentence-to-sentence matching. And what we want to tackle this problem is, okay, let's apply there's a many sentence-to-sentence matching in a language model, and we can just adapt that and apply this to the computer vision and see if we can make the line matching working nicely. So this is captured from our final work, and as you see, the lines are pretty well matched across the images. And as I said, we are treating a line as a set of words. It's a sentence consists of many words, right? This line, the visual line, consists of many visual words. And you see, if you look at the attention, you see very high importance is occurring at the corner point. That's actually obvious. And why we choose this line as a sentence matching, another key important aspect for that is when we try to match lines, there could be cases when the sentences are truncated, like line could be occluded when we are moving and when we are changing the viewpoint. So this is really nicely handled by the sentence-to-sentence matching. The previous work, they tried to cross the pixel distribution over this band over detected line, but our method incorporate the transformer to have this line descriptor. Here we have more simpler example. So for example, if this is a sentence with 4 words in it, we have each one of the visual words, we actually use a super point for this visual word, and we make this line consist of 4 different visual words and have the position encoding and use the transformer to encode this for us. So you might notice that this line descriptor is already very descriptive, and it can maybe directly use for the line matching, but we actually have another module right after that. We don't directly use this line descriptor directly, but we looking at this one in using a GNN. We try to look at the geometrical correlation among the line distributions, because what we try to do at the end of the day is the place recognition. So this is kind of really helped in doing so. So this is our final line descriptor after the GNN, after the line signature network, and this is what we use. For the line detection, we use the line segment detector, LSD, for the detection. And for the words, visual words inside the line, we use the super point. So the next to ask is how to train. So we apply this one both in a self-supervised and supervised manner. For the self-supervised manner, this is widely known technique. Using the homography adaptation is known homography, you know where the points will be in the other image. So you can use this one for the self-supervised manner. You can train our network in a self-supervised manner. And also, we use the ScanNet that has nice ground truth. So we also train the network in a supervised manner too. So in total, we secured pretty much abundant data sets for the training and also for the test data. And this is our qualitative result, and it's working fairly nicely compared to other existing methods at the time. But one thing that I want to make note is that this last column here, the outdoor visual localization. This is from the Oxford data set, because why this is important for us is because this one is showing us the generalization capability, because this is on-scene data set. And if you look at this one, if we consider the correct answer within 1 meter bound and 10-degree bound, then our approach could almost achieve 90%, which is very impressive, even in the on-scene data. So here's a live demo that I want to show you. So we freeze the first frame and I'm moving into the scene, and you see the lines are matched across the scene. There's a huge perspective changes, and this is quite cluttered environment within our student office, and you see the lines are matching, and this was quite working well. But I'm not saying we should use only lines, but what I want to say more is the line and points are really complementary, and if we use them both, really, then that really helps, because many cases, in certain portion of the image has point feature, abundant point feature. In certain portion of the image has more abundant line features. So if we use both, we can have well-distributed features, and that really helps in both optometry, place recognition, and line matching. All right. So with that, I want to move on to the second topic, how we want to combine the deep learning into the graph lens toward the robot manipulation. Basically, this is an object lens. The object pose estimation problem is to to estimate the relative transformation fixed off between the camera and a target object. And as you see, this bounding box is visualized over using the predicted mean that we got from the deep network. And this is very important. We want to reach out an object to grasp and manipulate, and we want to know how the object is at with respect to the camera. And some typical assumption that we have for this is we want if the object is asymmetrical or symmetrical in advance before actually reaching out, so that we can get the proper CAD model. But what we want to say is sometimes the asymmetric object may become symmetric depending on the viewpoint. For example, of this mustard bottle, this looks very asymmetrical, but if we change the viewpoint, then this becomes suddenly very symmetrical object. And what we want to do is we want to know when this kind of degenerate case happens by looking at this certain measure. So in this work, what we try to do is we try to estimate the uncertainty or confidence associated to each one of the axes, object axis. How we do that more specifically is we have this model, and they're associated primitive image that actually the three different axes, X and Y and Z, RGB. Each axis is color coded by RGB, and whenever we reconstruct this target object, we also reconstruct this primitive image. This primitive image will directly give you the orientation information about the object. So we are enhancing the orientation estimation perspective. But we are not only doing that, we can also look at the quality of the reconstructed primitive image to measure the uncertainty associated with each direction. So each one of these axes will give you we're kind of predicting the uncertainty associated with each direction. And at the end, what we can do is we can incorporate that as a covariance in our post-GraphSlam framework. So here I'm showing you the video again, but this time please look at this right-hand side. Here, how the primitive axes are reconstructed. They are well reconstructed when things are okay, but when the scene is becoming a degenerate case, you see this quality of the reconstructed primitive axis is getting worse, and you see this kind of measure of the uncertainty picks up the threshold, and this is indicating that we cannot really believe in terms of the X and Y axis. Only the Z axis is something that we can believe. So we can incorporate this information into the as a factor in a post-GraphSlam. And if we solve it, because this is an object lens, what we can see is a slant. So you see the landmark or object appears, and it moves a little bit, but as we make more measurements or look closer, then it stays there. For example, here on this small screen, it's being refined. You see things are moving a little bit, but as we make more measurements, it's kind of stabilized and refined. So this is something that we have done before, and now we are reaching out to more challenging objects like transparent objects. There are many transparent objects in our daily lives in a lab environment and recycling center, right? And the problem of the transparent object is really hard to detect those. So this group, the previous work was done by Dr. Jun, and together with Ayoung Kim, and they are working toward this transparent object manipulation and detection and object estimation. And actually, we have recently released our transparent object data set, and they are actually probably in that room. So if you want to ask more about this manipulation of the SLAM or transparent object data set, please reach out to them. They should be able to answer better than me in person. All right. So the last topic that I want to talk about is the thermal infrared images. So our group has been working on this thermal camera SLAM for a couple of years now. This is a result from when we run the direct SLAM for the thermal images from the thermal images. Thermal image has been known as the all-day vision. So you see the map is reconstructed nicely. We can estimate our trajectory regardless of the illumination conditions, day, night, and you see from this little thumbnail, the RGB image is very dark and it's really hard to see. You can probably apply the deep learning to enhance that, but thermal camera by naturally, it just gives you the nice infrared information, the temperature information, which we can use directly for the direct SLAM. It's just changing from the photometric error in the RGB to the temperature residual. So basically, things are very similar, and you can apply this one for the thermal camera. So we were working on that part, and we realized there are not enough data sets for the thermal images. So last year we published a data set, stereo thermal camera data set. This has stereo read of RGB and stereo read of thermal camera together with a LiDAR. LiDAR can be used as maybe sensor fusion and for the ground truth provide. So this data set has been captured changing the time of the day from the dawn to afternoon to the evening. So you see the temperature histogram is changing a little bit. So that we have a variety of the temperature distribution within our data set. We try to secure more and more real world thermal data set, but that was not enough. What we felt we want to do more, like many deep learning and many more with the thermal images, but we realized the data is still not enough compared to the RGB. So what we think is maybe we can use the well-labeled data from the RGB by distillation of the labels from the RGB images into the thermal images using the image-to-image translation. So there are, for example, if we want to train our thermal image for the optical flow, labeling optical flow is very tricky and difficult. But if there is well-labeled optical flow from the RGB images, what we can use is just change the RGB image to the thermal image through the image translation and just use the labels from the RGB. So that is the idea of doing this. Something that we wanted to make a note is we try to use a multi-domain, not the bi-domain, because you can think of the thermal image. This is thermal to RGB, so this might be a bi-domain, but it's not because thermal has many different distributions, like the one that you saw before, like day, night, evening. So many different styles can exist, and this multi-domain style selection really helped us to make a more realistic thermal images from the RGB. And here is a quick video, short video that we tried to compare to the bi-domain translation. This multi-domain really helped. We translated from the simulation images, but also from the real images that we have and many other real images that exist in the community. You can use this one. And what we did from it is in the result, we try to see if this one is working for the optical flow or object detection. And we are actually sending from that toward the more various tasks in the thermal image. All right, so here's the conclusion. So we want to tackle the long-term deployment, and we wanted to secure more robustness, and we're doing that in many different ways. If we can, as long as we can apply the SLAM framework, even including the manipulation task, we want to see high-level features like lines, or we want to see if we can combine certain uncertainty aspects into the postgrad SLAM, or can we change the sensor modality totally to the new hardware to see if we can overcome many challenges. So those are something that I wanted to highlight from our work, and this work has been supported by many sponsors. And for the manipulation, we have been working with Professor Jiwan Liu from KAIST, and for the translation, image-to-image translation, we have been working with Professor Young-min Jo from Seoul University. Yep, with that, I want to conclude my talk, and thank you very much.
Actually, Professor, I have a question.
Yes.
Have you considered applying your method to some challenging conditions, for example, the snowy day or smoking conditions? Since
that's a very good question. I didn't put it in my slide, but the motivation, why I started working on thermal and radar is we had a project to put a robot into the disaster environment with full of smoke and fire. So in that kind of situation, thermal camera can see better than the RGB, but still has some limitations. So we actually reach out further to the radars for that kind of case. So yeah, unfortunately, due to the time limit, I couldn't really talk about that a lot, but thermal camera has advantage in the more disastrous environment when the visibility is degraded severely. Yes.
Oh, I see. Thanks. So